Hi, Andrew. Hi, Thomas. Can you hear me? Can you see the screen? Okay. All right. Very good. All right. I'm gonna start with the solution of exam one. Let's see. I guess we don't have a lot of people today. Maybe everybody's ready for Halloween or something. Okay. So let's first look at the first problem in the exam. So what I'm testing is the basic micromechanics, which is the how do you estimate the property of composites based on its basic material constituent properties. So the question about estimate the 1, 2, 3, 4, 5, 6 property of lamina made of glass fiber reinforced polyamide matrix composites. So I gave you these data. This is a matrix property, polyamide, and this is the glass properties. And additional information are the fiber volume fraction, 65%. So I didn't really limit what method you use. You can use, they're for certain parameter, the different models. So we are E1 is typically the easiest one to get estimate very close to the true value. The E1 is the fiber direction velocity modulus. And it's better to estimate it using a void model. We talk about the rule mixture. There are two kinds of rule mixtures, right? There's the void model, the Roos model. One is a parallel, the other is series. Void model is for parallel loading. Roos model is for series loading. So as we discussed before in the lecture earlier on these topics, for fiber direction, it's better to use a void model. Okay, it's closer to the true value. Roos model will give you pretty high errors. Roos model is good for E2, not E1, E2, okay? So the correct answer, if you want to get correct answer, you want to pick this model for E1. So it's very simple. You figure out basically, so what I list over here are the equations we need to use. This is a void model, fiber property times fiber volume fraction, matrix property times matrix volume fraction, and this is the effective property. So we choose these. These came from the table, right? The fiber volume fraction 65%, matrix will be 35%. All right, and then fiber modulus is this number 85. This number. And the matrix is 3.5. As you can see, matrix much softer than fibers. Okay. All right, then you plug this number in. 85 times 0.65, 3.5 times 35%. The answer is 56.5 gigapascal. That is the E1 for this lamina. Okay. All right. All right, this is probably the simplest parameter to estimate. The next one for E2, there really is a tool. You can use the Roos model or the Halpin-Tai equation. So here I use both. The Roos model is this model. This is when the element under loading is in series, because you are pulling fiber matrix along the matrix direction. They're like acting in series. Okay. And this provides a better estimation when compared to void model. This is usually a lower bound of the properties. Okay. So the correct model to choose is Roos model, not void model for E2. Okay. All right. Again, just once you pick the right model, the rest is just plug and chug. So we have fiber volume fraction 65%, matrix 35, fiber modulus 8.85, matrix 3.5. See, this number didn't change. This is because the fiber and matrix are both isotropic. So their modulus in the actual direction and the transverse direction are the same. This is not the case for some other material. For example, graphite. Graphite, the transverse modulus will be different. So you gotta pay attention to this. So for glass, we choose is 85, 85, right? This both number 85. For the matrix, the same thing, 3.5, 3.5. So there's no difference here because the material we're working on. This is isotropic, okay. All right, again, we plug these number into this equation. So this is inverse of inverse, sum of the inverse and inverse. So here is a inverse, sum, and inverse. And E2 we estimated using this model, Roos model is 9.29 gigapascal. Okay. All right. Also, we learned in the lecture that this usually is the lower bound. So the true value is somewhat higher than this. Okay. A better model for estimating E2 is Halpin-Tsai equation. All right. This is the equation that actually give a much better results. As we see the comparison with experiments, this is probably the best out there that you can choose to do the estimation. So this model is the empirical model. There are some parameters you gotta fix. One of them is a reinforcing factor. This factor is a curve fitting parameter, usually between 1 and 2. For hex array packing with high VF, it's 1. For low volume fraction square packing is 2. So if it's closer to square packing, low volume fraction, you can pick somewhere in between 1 and 2, close to 2. So here our problem state that we have close to hex packing, right? Like this, and the volume fraction is fairly high, 65%. So for this reason, we pick Kasi equal to 1. All right. So Kasi was picking this value was chosen due to the information we're given. Okay. And then we can go ahead and calculate this factor eta. Eta is what you required here to calculate this. Eta is just a combination of modulus and Kasi. So we plug these number into this equation and also Kasi equal to 1. We can calculate this parameter eta equal to 0.921. Right. Then you stick eta and Kasi back into this equation. You calculate this right-hand side fraction, which also involve fiber volume fraction, which is 0.65, which is over here. This is the entire equation here. And then you multiply EM. EM is a matrix modulus right here. Multiply EM, then you have E2. And this E2, as you can see, is a little bit higher than the Roos model. This is a better prediction. Okay. It's a 13.9 gigapascal. Remember the Roos model we applied is 9.29. Okay. I mean, if you use either one of the model, I will count it correct. It doesn't really matter. You just pick 1 and 2. If you pick a void model for E2, that'll be wrong. If you pick Roos model or the Halpin-Tsai equation, both are correct. Okay. Halpin-Tsai again is slightly better than Roos model. Okay. Any questions so far? All right, so where are we now? So we estimated E1 and E2. The next thing we want to estimate G12. G12 is in-plane shear modulus. G12 is very similar to E2, is material loaded in series, not in parallel. Okay. So if you want to rule a mixture, you want to pick the Roos model, this model. Again, another choice is Halpin-Tsai equation. Okay. So again, I did both. I first applied the Roos model, which is a ruler mixture. So this is the input parameter. So we got to use fiber shear modulus and the matrix shear modulus in these calculations. They came from here. The shear modulus for fiber is 35.42, right? This number here. Shear modulus for matrix is 1.3, right? 1.3. And then we have volume fraction, which is the same, 65%, 35%. And that goes into this equation right here. And this is the result here. So in-plane shear modulus is the inverse, sum inverse of the inverse, right? Inverse of the sum of inverse, weighted by volume fraction. We have 35%, 1.3, and 65%, 25.42. It turns out that G12 is 3.4 gigapascal. Okay. Now the choice of unit, whatever you choose here, whatever you enter, whatever you unit for GF, you want to use the same units for GM, and then your result G12 will have the same units. Because I use the gigapascal, right? So both my output will be gigapascal as well. Okay. Now if you put a, 25 e power 90 here, and then you'll get a Pascal out of here. Okay. Any questions? Make sense? All right, so we apply Roos model of G12. The alternative for Roos model is Halpin-Tsai equation. We discussed this in the lecture again. It's very similar to Halpin-Tsai for E2. This is the equation for G12. We need two parameters, reinforcing factor and then eta factor. The reinforcing factor for shear modulus is predicted by this empirical equation. You take volume fraction raised to the power 10 times 40 plus 1 that you could see, right? So we first calculate that parameter because we know the volume fraction is 65%. So it's a very simple calculation. You just plug and chug, you put everything in there. 65% raised to the power 10 times 40 plus 1. This is dimensionless because this is a VF the ratio. So the whole thing is dimensionless. So it turned out to be 1.54. Okay. And then you use the cassette to calculate eta. Eta is another parameter that's needed in the final equation. So I pre-calculated eta. I just stick this number in, GF, GM, ratio, and then -1 plus cassette, and then my eta is 0.912. Finally, cassette and eta go into this equation, which allow me to calculate G12. G12 is, this is a GM, 1.3. Multiply this whole fraction is this fraction right here. So this gave me a prediction of a 6.194 gigapascal. This is a G12. All right, you can compare this G12 with what's predicted on Roos model. You find that this is a little higher too, which makes sense because we know the Roos model usually is a lower bound. So the true value is usually slightly higher than Roos model. As you can see here, in both cases, when you use Halpin-Tsai equation, you get slightly higher predictions. 6.2 here versus 3.4, and in case of E2, it is 13.9 versus 9.29. Okay. And the Halpin-Tsai equation has been proven to be closer to experimental values. All right, any questions? Next, we are onto this two thermal expansion coefficients, alpha 1, alpha 2. Alpha 1 is thermal expansion in the fiber direction. Alpha 2 is in the transverse direction. So we know the thermal expansion of the fiber, which is 5 ppm per degree C, which is given here, 5. And the matrix really is 90 ppm per degree C. It's much higher. So 1 micrometer per meter is 10 to the minus 6, right? That's the 1 ppm per degree C. Okay. All right, to do that, we use the micromechanical models. This is also given in the lecture slides. Is really there's a one equation for alpha 1, another equation for alpha 2, and this is a fiber direction, thermal expansion. This is a transverse. As you can see, you need a modulus. You need E1. So we need to use the E1 we predicted right here to calculate alpha 1. We need this number. This number need to be used. Okay. All right. That number is oh no, that's E2. E1 is 15. E1 is 56.5. Okay. So that's the E1, and then EF is fiber Young's modulus, EM is matrix Young's modulus, and VM and VF are volume fractions. Alpha F, alpha M are the thermal expansion of fiber and matrix. So I listed them all here. This is what's read off from that table given. Fiber thermal expansion, matrix thermal expansion, volume fraction, fiber modulus, matrix modulus, and then the Poisson ratio for fiber and matrix. Okay. So to do the first one, I just do plug and chug. I can, this is the results. I plugged in, basically, I use the ppm units for alpha, so the result will be ppm as well. I use gigapascal for EF, so I'll also use gigapascal for E1. If all the E are same units, it cancels out. What you don't want to do is use one unit for EF here and use another unit for E1. That'll give you pretty big errors. As long as you use the same units, they'll automatically correct itself. They'll cancel out whatever factor you use. So here I use all gigapascals. Okay, my EF is 85 gigapascal. EM is 3.5 gigapascal. My E1 is 56.5 gigapascal. Okay. Yeah, by just plug and chug, everything is factored in. I got 6.84 ppm per degree C, or you can write 6.84 micrometer per meter per degree C. Doesn't matter where you write, but it's as you can see, it's a little bit higher than matrix, than fiber. Right, that makes sense because the matrix is much higher than fiber. So this bring up the fact that the matrix material expands more than fiber actually make the one direction expansion slightly higher than fiber. Again, it's fiber dominated. It's much closer to fiber than matrix. Okay. This is the E1, alpha 1. Okay. For alpha 2, we got to use this equation. This is a transverse thermal expansion. And this equation requires alpha 1 that we pre-calculated from this equation. Also require a parameter nu1, 2, which you need to pre-calculate to use this equation. New fiber, volume fraction fiber, new matrix, volume fraction matrix. I have a new fiber, new matrix read off from the table. Right, these from the table here. The new fiber is, this is the fiber is the Poisson ratio is 0.2, right here. Poisson ratio for matrix is 0.35 right here. So this was required. So we plug them in. Also plug the prediction I had before, alpha 1, and also the new 1, 2. New 1, 2 is the effective Young's modulus of the layer. So use the Voigt model rule of mixture. It turned out to be 0.2525. So this number goes in here, alpha 1, and these numbers all combined together. This give me thermal expansion in two directions to be 44.7 ppm per degree C. Okay. As you can see, it's closer to 90. It's closer to matrix, but a little bit less due to the impact of fiber. Fiber kind of bring this down a little bit to 44.7. All right, any questions? All right, now the last part. Not is this, that's the last part. Yeah, the last part we need to predict is the tensile strength in the one direction, F1T or sigma 1T. All right, so that number is predicted based on the assumption that the lamina will break at the same strain as the fiber breaks. This is the rationale. The composite will break at the same strain as the fiber. Fiber has a fracture strain. When you stretch fiber to a certain strain, maybe a few percent, 1% or 0.5%, it breaks. So most likely the composite will break once the fibers start breaking. Okay. So in order to estimate the strength, we first need to figure out what kind of strain the fiber will start breaking. We can estimate based on the fiber strength. The strength of fiber is 1.5 gigapascal or 1550 megapascal. And the Young's modulus is 85 gigapascal. I came from here. So 1550 is a tensile strength right here. 85 is the modulus. So you can calculate the strain. The strain it takes for the fiber to break is the ratio of these two numbers, right? I made a conversion from the gigapascal to megapascal because they're factor difference, 1,000 differences, right? 1 gigapascal is 1,000 megapascal, right? So the ratio is the failure strain. So it turns out that the failure strain for the fiber is 1.82%. 1.82%. All right. Now we have everything we need to predict the strength of lamina. Uh, 35. Thank you, Andrew. Did I make it around 35? Oh, yes. Thank you, Andrew. Yes, I used 25. Did I use 25? Yeah, I copied wrong. You're right, Andrew. It's 35. Yeah. Let me quickly correct this. This is not good. Let me correct this. 0.65 divided by 35.42 plus 35 divided by 1.3. All right, it's a 3.477. 3.477. All right, that number, and then if I got this wrong, I probably got this wrong too. I got this wrong too. 35. Oh, I got this wrong here. I got this correct here. 35.12, 35. Yeah, I make this number, I think is right. I use 35. I wrote 25 here, but I use 35 correct number here. So okay, thank you very much for letting me know. Okay, let's get back to this. We're calculating the tensile strength one direction. So we just plug and chug. We put the number in here. The fiber strength 1550 megapascal. So here I use a megapascal for everything. So my result should be megapascal. So my EM is also, see here I convert to megapascal. It's a 3.5 gigapascal. I multiply 1,000 so that the EM is in megapascal to be compatible with the megapascal here. Okay. And the epsilon F has no units, so 0.0182, which calculate from here. And the volume fraction, no units. So everything should be megapascal. So once we get everything in, we calculate number is turns out to be 1030 megapascal. This is the strength in the one direction, the strong direction of this lamina. Okay. Any questions? So that's all 5 numbers, 5 or 6. Let's see how many. 1, 2, 3, 4, 5, 6 numbers we predicted. Among them, 2 of those can be predicted with either one of the 2 models. There's choices. Okay. All All right, let's do the second problem. The second problem is basically do some very simple CL classical laminate theory calculation. So basically, I ask you to calculate ABD of a two laminate. One of them is glass epoxy layup here, and the other one is a symmetric layup graphite epoxy. I give you the lamina property here. So this column is glass epoxy, and this column is graphite epoxy. You gotta pick and choose the right input to your code. So these are all the input to your CLT code. You gotta modify your lamina properties using this properties, and also the layup need to be entered in your code, and then you can just calculate. I also ask you to calculate the stress in the 0-degree layers when lamina is being pulled at this load, 30 pounds per inch. And I ask you to estimate the percentage load taken by the 0-degree layers. There are two 0-degree layers, right? The first layer and the last layer. So you gotta add them up. There are two layers, right? All right, so it's very simple. You should have, before you enter the exam, you should have a working CLT code. I have you worked for a few weeks. You should also calibrate it with some standard inputs. So all you need to do is basically key in the inputs, which are just two blocks here. One of them is the layup, the other is the layer properties, right? That's what you need to put in. Okay. Now, when you're doing the exam, I saw a lot of you are struggling with units. Your CLT code should be unit neutral. At least that's what I recommend you to do. You shouldn't take a certain unit system and then just freeze it. You should make it unit free, because all the equations are universal. They work with all units. As long as, let's say you use a PSI inch system, pound PSI inch system, you shouldn't need to make any unit conversion. You just put in a set of a consistent unit in. You stick for any length, you stick with the inch. That also includes the thickness of the lamina. Any stress, you stick with PSI. Any load, you stick with the pound or pound per inch. It should give you the right result. So that's the best way. Now, the same code, exact code, you can just stick in different units. Let's say you decided to use Pascal for your modulus, and then you decide to use a meter for your length measures, and then Newton for your force, and then you don't need to change anything. It should just work. So that's the best way. You should have your code unit dimensionally neutral. You don't want to freeze up. All the input has to be this units. It's too rigid. Okay. All right. I can show you where my code is. Where did I do it? All right. So here is. Where did I put my? Desktop. Well, I lost my code. I don't know where I stopped it. But anyway, I have the results here. I'll just go over results. And I lost the. I don't know where I put my spreadsheets, but I just typed these in. This is ABE matrix for the first laminate. This is a 6 layer. This is input and this is output. So since I input with see, I use PSI, I use inch. So this will be the corresponding. This must be PSI. This units. Okay. These units are complicated. Has to do with the curvature. Curvature should be 1/inch now. So these are some compatible units with the pound inch system, whatever it is. My code is unit neutral. Now that's basically very simple, plug and chug. What you don't want to do is you just converting your unit like crazy. You just convert here to a megapascal, gigapascal, and then you fix your code with a Pascal, and all those things become messy, and they're very easy to make mistakes. So make your code dimensional neutral. And then the second part of the question is figure out the percentage of load taken by the 0-degree layers. All right, so we need to calculate the stress in each layers. In order to estimate the load taken by the layer, you need to calculate the stress in that layers. And you multiply the cross-section area, that's the load taken by that area, right? All right, so the tensile load applied is tension in the x direction is 30 pounds per inch. Okay. Now, if the laminate is 1 inch wide, it will be 30 pounds, right? If laminate is 2 inch wide, it will be 60 pounds, right? It's 30 pounds per inch. So when I apply the load here, this is the load I apply to my code, which is oops. This is the load I applied. I apply only a single tensile load, 30 pounds per inch. And then I read off the stress in my layer 1 and layer 2, layer 6. These are the 0-degree layers. Because I asked you to estimate the load, the stress, the load taken by these two layers. So I need to know the stress in there. In particular, I need to know the stress in one direction. It turns out that layer 1, layer C is basically having the same stress. So based on my calculations, they have the same stress. This is that stress, exactly the same. And what's important is this value. This value is, because I use PSI, this is a 448.7 PSI. So Andrew, I have a question here in the chat window. So oh no, if anything is 10 to the power minus 10 is 0. Yeah, I agree with you. That's a very small number, it should be 0. That's fine, Andrew. All right. Now let me calculate the fraction load taken by the layer 1, layer 2. The way you calculate it is you multiply the stress by the thickness of the layer, which is the total thickness, because they have the same stress here. I just calculate them all together, combined way, right? So the total thickness of 2 layer is, what is it, 0.04? Each layer is 0.02. So I take the stress, multiply the thickness, 0.04. That will be the load, linear load density taken by the layer 1 and 6, right? Right. This is combined thickness. They have the same stress. They are 448.7, right? 448.7. And then I divided this by the total load. Total load is 30 pounds per inch. If you can imagine the laminate is 1 inch, then the total load is 30 pounds. And then the total area is 0.04 inch. It's 0.04 times 1 inch, right? That's the cross-section area. You multiply that with 448, right? That's the load. The ratio is almost exactly 60%. It's a 59.8%. You can round out to 60%. So that's the load taken by the first and last layer, which has a 0-degree orientation for this laminate. All right. So that's we finished the calculation with this glass epoxy laminate like this. And the next thing, we calculate the CLT ABD matrix for this graphite epoxy laminate. We're gonna use the property here. The difference between glass epoxy and graphite epoxy is, in graphite epoxy, your E1 is much higher. because graphite is so much stiffer than glass. So you see the big difference here. The graphite epoxy, the E1 is 26.25. MSI is a million PSI. MSI is a million PSI. KSI is a kilo PSI, is a 1,000 PSI. So 26 million PSI is the E1 for graphite epoxy laminate. So 26 million right here. This is what I input to my code, right? This is graphite epoxy, E2, new12, G12. My new2 is calculated automatically. Actually, I only type in 4 numbers: E1, E2, new12, and G12. New2 is generated. I didn't need to type in. It will calculate it based on the reciprocal theory, reciprocal identity in the lecture. You can look for that. Look up that. So material property, and then layup. Layup is a symmetric layup. So I have 6 layers: 0, 60, minus 60, minus 60, 60, 0. Okay. Thickness 0.02 each one. And this is my ABD matrix. With these, I just do the multiply and sum, things like that. So basically, these will be zeros. These will be essentially 0, 0, 0. Okay. So my B matrix essentially is 0 matrix. This is a 0 matrix. Everything is 0 here. Okay. For this layup. Okay. But A and D matrix are non-zero. You see A and D matrix they're non-zero. This is non-zero, non-zero. Okay. All right, that's ABD. Again, because I use a PSI, right? My units here, that's PSI. Okay. This is not PSI because now we have a curvature factored in. This is to do with the curvature units. Okay. And this is my stress calculation. When I apply load 30 pounds per inch, I can calculate the stress in each layers. And then I read off the stress from the first layer and the 6th layer. Those are the 0-degree layers. Okay. This is my first layer. This is my 6th layer. Notice I have 2 columns. The first column, this column, is on top of the layer. This column is for the bottom of the layer. If you do the average, that'll be the middle layer. So top, bottom. Okay. For this case, turn out the top and bottom are same stress. Top, bottom of layer 6. Also, my layer 1, layer 6 see same stress. So that stress is 49.4. I type run again. 649.4. All right. Sigma 1. Same idea. You calculate fractional load. You take the stress 649.4, multiply the total thickness of layer 1 and 6, which is 0.04, and then divided by total load. In this case, is 86.6%. So for the second laminate, the first and 6th layer takes most of the load, if not all the load. Most is more than the glass laminate. All right. That's it. That's the 2 problems that we in the test. Any questions? All right. If no more questions, I'm gonna switch topic to the hygrothermal stress, which is the next thing I want you to implement in your CLT code. I want you to each one to work on this, to put in the to basically add this functionality in your code. I want to go through the this is already in the slides in the classic laminate series. We have a set of slides on CLT. This is the last part of it. I think we went through part of it one day, but I don't think we went through examples. but I want to repeat one more time. Have you start working on this? I'm gonna focus on discussing how do you implement. So what are the input needed? How do you make that work? So to do the hygrothermal stress calculation, which is very important because most the epoxy carbon or glass epoxy, once you have the panel made, there's already pretty high stress built in there due to the manufacturing process. So then you apply additional load, then the stress in the laminate in each layer is a combination of your fabrication induced stress plus your external load induced stress. Okay, it's a combination of those. All right, so to start doing the hygrothermal stress analysis, you got to know the thermal expansion coefficient for each layer. Okay, which is here. Where is that? All right, I had that earlier. Maybe I have it. Where did I put it? The alpha. I lost my alpha. All right, so I need to add one more slide on there. But anyway, I want to explain verbally. So you start with alpha, which define the lamina expansion property in 1-2 direction. Okay, you start with that. That's involve alpha 1, alpha 2, basically. And then you transform alpha into the XY coordinates. The alpha transform exactly the same way as the string transform. You transform alpha the same way as string transform. Then you obtain this alpha in XY coordinates system, which is here. So you got alpha in XY coordinate system. Okay. And then you calculate something called a effective load. We use a subscript or a superscript T for it. So basically that's the load due to the insides of this layer try to expand different ways. Okay. Which is calculated using this equations. That equations, this set equations. So you start with alpha 1, alpha 2, and you transform alpha into XY coordinates, and then you use this set equation to calculate two vectors. The two vectors are called NT and MT. These are not the true load. Remember, we use N for force load, M for moment load. These are hypothetical load. These are not true load. These are basically represent that there's thermal stress at self-equilibrium. That's what these two equations mean. These are equilibrium equations. Okay. But you calculate these anyhow. You basically have alpha of each layer. K is each layer. And then you multiply the matrix, this Q bar matrix, stiffened matrix, and then you sum, multiply the thickness, and you get NT matrix. And here you get MT matrix a similar way, but you multiply different parameters. You multiply this square difference. You also multiply delta T, and so you also need to know delta T. So in order to calculate hygrothermal stress, you have to know what is the change in temperature from your stress-free temperature. Stress-free temperature is a reference temperature. People assume at that condition, there's no thermal stress. Everything is in its most free state. That usually is somewhere between the curing temperature and the glass transition temperature. It depends, but it usually is high. It's higher than room temperature. Somewhere it could be 50 degree above, 70 degree, or 100 degree above room temperature. There is a temperature there where things are assumed to be stress-free. Okay. All right. So you need that number, and you need a thermal expansion for each layer, and you build this into your code. Your code basically calculate two vectors. All right. Any questions so far? So you need to start programming this into the code. Okay. Now, once your NT and MT are calculated, you can solve for this vector here, epsilon and kappa. These are the thermally induced deformation and warping. Okay. You solve this matrix equation similar, exactly the same way as you solve the matrix, the laminate deformation during internal load. You're just using a hypothetical thermal load. These are not true load. These are hypothetical load. Okay. These allow you to solve this 6 variables is a 1 by 6 vector. This represent what happened to the laminate once you cool from a certain high temperature by delta T to another temperature. This will be the warping. K is warping. Epsilon is the stretching or shrinking of the laminate. So just by solving these vector, you can tell how bad this laminate will warp due to the thermal stress. Okay. Warping is a big problem when you deal with fabrication of laminate. You lay things up, you vacuum bag, you put in the mold, you cure it, take it out. Once you peel it off the mold, it become all twisted, and that's warping. That's due to the infight of the different layer want to stretch or span different amount in different directions. Okay. And your CLT code, if you implement these two vectors, you calculate this kappa, this is 3 number here, are the warping factors. One of them is twisting, 2 of them is bending. Okay. All right. And then if you have additional mechanical load, you can calculate additional deformation. You can superimpose your mechanical load with hypothetical thermal load and calculate the total strain. Or you can do it separately. You can calculate the strain due to mechanical and combine with the strain due to thermal and get a 2 strain. So basically, your mechanical strain is the total strain times thermal strain, or your total strain is mechanical strain plus thermal strain. Okay. All right. Let's look at example here. This is a example. You can, once you implement your hygrothermal model, you can check with this example. You can type in the input here and then see if your code predicts the same way. Okay. So this is the 2-ply laminate 090 graphite epoxy. And you have a temperature change in the minus 75 C. It basically you're cooling this thing down from stress-free temperature by 75 degrees Celsius. And then each lamina is 5 millimeters thick. So you calculate the thermal expansion is in 1, 2 coordinates is this much. Fiber directions less, transverse direction much higher. And then you transform that into XY directions. Okay. This is for 0 degree, this is for 90 degree. You transform that. And then you figure out a Q bar for each layer, and you calculate the hypothetical vectors, load vectors. by using this set of equations. This set of equations, okay, which is here. You basically calculate. This is for one layer. This is the second layer. You sum them up, and this is your hypothetical load due to temperature change. Okay, and this is your hypothetical bending moment. Now, remember the differences here are. This is a difference. This multiplier is a thickness of layer. This is a square difference of the location. All right, this is a different. This is kind of similar to how you calculate your ABD, right? Okay, so you get M and N, and you put them together. ABD is calculated the same way as before, and you can then come to this governing equation. This is your hypothetical thermal load to the left-hand side, ABD matrix, and that's your mid-plane strain and curvature, and you can solve it. You solve this set equation, you got basically a stretching and warping. So this calculation predict that this laminate cross-ply 0-90 degree will warp. This actually predict which way it'll bend. It'll bend in X and bend in Y. It'll stretching as well. It's not going to shear. This gamma XY equals 0 means it's not going to shear, and then KXY equals 0 means it's not going to twist. The last term kappa XY is a twisting. So it's a curving but not twisting. It's stretching but not shear. Okay. This is a thermally induced strain. All right. And you can also calculate thermally induced stress. Then you have you calculate the mechanical stress. You calculate the total strain each layer. This is the total strain each layer using what is a Kirchhoff assumption. This is a Kirchhoff assumption that we learned at the start of CLT. So using this set of numbers, mid-plane stretching and the curvature, you can calculate total strain anywhere in the laminate. You just use, let's review Kirchhoff assumption. Kirchhoff assumption is this. It's one of the cornerstone of classical laminate theory. You can say that a classical laminate theory is built on Kirchhoff assumption. This is the Kirchhoff assumption right here. Okay. And this is the vector form of Kirchhoff assumption. It basically says, if you know the location of a certain lamina in Z direction, and you know the mid-plane stretching and curvature, you can calculate the strain anywhere. Right, that's strain anywhere equal to mid-plane strain plus a modifier. Height of each layer multiply the curvatures. Okay. So we back to this. Once you figure out the total strain under hygrothermal conditions, you reapply the Kirchhoff assumption to calculate the total strain. That's the Kirchhoff assumption. Where is that? Right here. All right, so we know the total strain from Kirchhoff assumption. And then you also know the thermal strain in that layer. The thermal strain is basically alpha times delta T. This is a free thermal strain. If you take the laminate, this layer out of the laminate, you let it free expand when you have a minus 75 degrees C temperature change, this will be the strain. Okay. All right. We also know that the total strain is a thermal strain plus mechanical strain. So we can figure out a mechanical strain. Mechanical strain will be total strain minus thermal strain, because mechanical plus thermal is total. If you know the total, you know the thermal, you subtract thermal out of the total, you got mechanical. Okay. And the mechanical strain is what causes stress. Only mechanical strain is related to mechanical strain is related to mechanical stress. Thermal strain is due to temperature change, so this is not related to stress. So then you can plug in the mechanical stress into this Hooke's law. This is a Hooke's law, right? mechanical strain multiply the stiffness matrix. This is almost like a Young's modular times strain equal to stress. This is analogous to that. And you can calculate your mechanical stress in XY coordinates, which is this value. And you can transform that back to the 1-2 coordinates using the same transformation equation you had before. So this will be the stress in each layer due to thermal effect. This is a thermal mismatch stress. Remember, the laminate, we didn't apply any external thermal load. We just let layer fight. Due to the fact that these layers try to fight each other, they produce internal mechanical stress, which is produced by this, calculated by this. And in summary, you can calculate for both layers. You know, what's the mechanical stress, what's the mechanical strain, like this. And this is only thermal effect. When you do the combination of stress, external mechanical load plus thermal stress, you do a superimpose. You put load-induced stress with the temperature-induced stress together. That will be your total stress. All right, so that's basically the workflow. So start working on this now. We'll give some time, then we'll start solving some problems with thermal stress factored in. All right, does it make sense? Any questions? Now, if your CLT code is has a rigid units, I suggest you change that now. Don't modify your code so it doesn't fix on a single set of units. Make it unit neutral. Especially you want to use later for your own research. That's much more convenient to use than you have a fixed units. Any questions about thermal stress? Now we say high-growth thermal stress. High-growth is the thermal, it's expansion due to absorbing water. It's basically can be computationally taken care of in exactly the same way as the temperature effect. So in the example, we saw thermal effect, but you can do a parallel high-growth effect as well. But I will not require you to do that in this class, but you understand that basically exactly same method. And you look at the typical material properties that are given in the table, you find that see the coefficient of moisture expansion is high-growth effect. It's very similar to thermal expansion. See the transverse coefficient thermal expansion, and then the fiber actually not affected by the water content. The matrix is. The matrix has a coefficient of moisture expansion. This is the high-growth part. You can deal with high-growth part in exactly same mathematical form as thermal. So if you know how to model thermal effect, you know how to model moisture effect too. There's no difference. Any questions? You can either type in the chat window or you can speak up. All right, if no question, I'm gonna stop. I'll let you go. Enjoy your holiday weekend. I'll see you guys. See you guys on Monday. All right, you all have a good weekend. Bye bye.